We're going to discuss limits at infinity. So we're interested in pretty much the limit as x tends to positive infinity of some function f of x, and also the limit as x tends to negative infinity of some function f of x. Now, what is interesting is that we can give a pretty simple graphical interpretation of those limits. So for example, if somebody tells us that the limit of a function at positive infinity as x tends to positive infinity is 2, then we can imagine a function that as x becomes larger and larger, its outputs approach the number 2. Thus, the graph almost aligns with the horizontal line y equals 2. So this is the horizontal line y equals 2. And in this case, so if the limit as x tends to a of f of x, as x tends to infinity of f of x is a, then the line y equals a will be called a horizontal asymptote for f of x, or for the graph of f of x, we could say, at positive infinity. Similarly, if the limit as x tends to negative infinity this time of f of x is, let's put some other letter. The letter doesn't really matter. We could still put a. I'm going to put b just to suggest that if anybody thinks that it's the same function f of x, that there's a possibility that we could get two different limits. Then the line y equals b will be called a horizontal asymptote for f of x, or the graph of f of x at negative infinity. And finding these limits will resemble very much how we did things for sequences, because with sequences, the variable n approached infinity, and here we have pretty much the same case where the variable x approaches positive or negative infinity. So it would make sense to work out some examples with rational functions. And as our first example, let's take the limit as x tends to infinity, positive infinity, of 3x squared plus x minus 1 over 5x squared plus 6. It's not hard to imagine what needs to be done here. We're going to pretty much work in exactly the same way as we did for limits at limits of sequences. So we will factor out x squared, and we will have 3 plus 1 over x minus 1 over x squared, and x squared times 5 plus 6 over x squared, actually. And now we can cancel out the x squares, and we're going to get the limit as x tends to positive infinity of 3 plus 1 over x minus 1 over x squared divided by 5 plus 6 over x squared. And now we're going to work this out exactly the same way as we did for sequences. So this tends to 0, that tends to 0, this tends to 0, this tends to 5, this tends to 3. So the whole thing tends to 3 on the top, the whole thing tends to 5 on the bottom. So the final answer here is going to be simply 3/5. And that's going to be the case for any rational function at either positive or negative infinity. So here, just to see how the notion of horizontal asymptote is used, we could say that the line y equals 3/5 is a horizontal asymptote for the graph of f of x equals 3x squared plus x minus 1 over 5x squared plus 6 at positive infinity. And we can also guess here that when the degree of the numerator is less than the degree of the denominator at either positive or negative infinity, the limit is going to be 0. Why? What would we do here? Usual story. So we will factor out x squared, and we will have 1 plus 1 over x plus 1 over x squared, and divided by x cubed times 1 plus 1 over x cubed. And this can be rewritten as the limit as x tends to negative infinity of 1 over x times 1 plus 1 over x plus 1 over x squared over 1 plus 1 over x cubed. And it's very easy now to see that this tends to 1 and this tends to 0. So the whole thing will tend to 0. That will be the limit. If we want something slightly more interesting, then we should turn to the case where the numerator has degree larger than the denominator. This is where we can have all sorts of interesting cases. So let's take, for example, the limit as x tends to negative infinity of 3x squared plus 1 over 5x plus 2. Let's see what this limit would be. And again, the same strategy will work here. So just factor out the largest term from numerator and denominator. So this will give you x squared times 3 plus 1 over x squared divided by x over 5 plus 2 over x. And again, this here, there will be a nice cancellation. So x squared and x cancel to give us, simplify to give us an x. And then we have 3 plus 1 over x squared divided by 5 plus 2 over x. This whole thing tends to 3/5, but this one now tends to negative infinity. And here you would get either negative infinity or positive infinity if you have a power of x. If the power of x is even, you will get positive infinity. If the power of x is odd, you will get negative infinity. And of course, the product will tend to negative infinity, and that's what the limit is. I mentioned before that there are cases in which we can have a function for which the asymptotes at positive infinity and negative infinity are different. And here's a very, very simple example. So maybe the simplest example we can come up with here is something like x over absolute value of x plus 1. I think this is a really, really simple example. If we take the limit as x tends to positive infinity of x over the absolute value of x plus 1, then since x becomes eventually positive, that should give us, we can replace the absolute value of x by x because we're interested eventually in positive numbers. And when we find this limit, factor out x from the top, factor out x from the bottom, 1 plus 1 over x. These two things cancel each other, and you will get limit 1. Yes, but if you do this at negative infinity, what changes at negative infinity? Well, since we eventually deal with negative numbers, the absolute value of x will be negative x. So negative x plus 1. And here, when we factor out the largest possible powers, what we will get is negative 1, because we have this negative 1 right here. So you have 1 on the top, negative 1 on the bottom. That gives you negative 1. So the function f of x, the graph of f of x, has the line y equals 1 as a horizontal asymptote at positive infinity, and the line y equals negative 1 as a horizontal asymptote at negative infinity. So I would like to finish with a very interesting limit. We'll do a limit of not a rational function, but we're going to use some of the principles that we have seen so before. It's a very interesting limit, though. We're going to find the limit as x tends to positive infinity of square root of x squared plus x minus x. So how are we going to do this? Obviously, we can see here that we have two quantities, both of which tend to infinity, this quantity and this quantity, and then we take their difference. This is the standard case in which we say that we have an indeterminacy, meaning if somebody tells you that I have a quantity that tends to infinity, another quantity that tends to infinity, and I subtract them, if you don't see the quantities, if you don't do something, there's no way you can answer in general what the behavior of that function is going to be. So to resolve this indeterminacy, to raise this indeterminacy, what we're going to do is multiply and divide by the conjugate quantity. And this will give us the limit as x tends to positive infinity of square root of x squared plus x squared minus x squared over square root of x squared plus x plus x. So this will be the limit as x tends to positive infinity of x squared plus x minus x squared divided by square root of x squared plus x. Do this first cancellation. Let's write it once just to look at it and think what we can possibly do in this case. And the answer is that the general idea that we employed in the case of rational functions, factoring out the largest possible quantity from numerator and denominator separately, will actually work very nicely here. And how are we going to do this? From the numerator, really, you have just x. Write it as x times 1 so that if we do a cancellation, we know what is left behind. On the denominator, we have to be a little more careful. So what I'm going to do is factor out an x squared from inside this square root. So I will have 1 plus 1 over x here, and then plus x. And in the next step, I'm going to take that x squared outside the square root. And what will happen is we will get x. So it will be x times 1 plus 1 over x plus x. And this is going to be the limit as x tends to positive infinity of x times 1. And now we can factor it out, and we will have x times square root of 1 plus 1 over x plus 1. I think I'm giving the steps in a what could be described as a really detailed fashion, maybe too detailed. But we're ready to find the limit either way. So the only thing that is variable here is this 1 over x that clearly tends to 0. So on the bottom we have 1 and 1, that's 2. So the final answer here will be 1/2. A very, very interesting and fun limit to consider. And that completes our work. Thanks for watching.